Dear students and members of the Faculty Search Committee, I am Yasir Malkani, candidate for teaching faculty at the Florida International University. Today, I am presenting a short lecture from the course Secure C Programming for Engineers. Over the next 15 to 20 minutes, our focus will be memory safety and buffer overflows. The prerequisite for this course is C programming fundamentals, especially the concepts of strings and arrays. Let's start with the learning outcomes of today's lecture. By the end of this lecture, you should understand why secure C programming matters, how C manages memory, what buffer overflows are and why they occur. You will also be able to identify vulnerable C programs that may cause buffer overflows and their impact. And finally, you will learn some safer C coding practices to prevent buffer overflows. So let's begin with why secure C programming matters and why should engineers care about secure C. So there are several reasons for why secure C programming matters. Firstly, C is widely used programming language in Internet of Things embedded in cyber-physical systems. Many systems developed in C are embedded in home appliances and are also used in vehicles and in many medical devices, and are also part of many critical infrastructures. And due to this, any vulnerability in these systems can have severe consequences, ranging from system crashes to financial losses and even life threats. Another reason is C's direct memory access feature. At the one hand, C's direct memory feature enables high performance, but at the other hand, it also introduces some serious risks. And if we look at the historical data, many past attacks like Morris worm and code raid exploited unsafe C code. And also note that failures in engineering systems can be much more disastrous. I mean here, in engineering systems, failures are not just software bugs, but they can have real physical and safety consequences. So therefore, being an engineer, it is our responsibility to develop systems which not only work well, which not only functional, but those systems must be safe and resilient. So before understanding buffer and buffer overflow, let's have a look on C memory organization. C memory is organized into stack, heap, buffers and arrays, and pointers. Stack is used for local variables and function calls, and heap is used for dynamic memory allocation and deallocation. Buffers are fixed size memory blocks that help in storing and processing large amount of data, while pointers are used for direct memory access. So now let's understand what is buffer and buffer overflow. So at its simplest, a buffer is basically a consecutive block of memory that is used to store data like strings, text, or even sensor readings. For example, when you write char name 10, you are basically reserving exactly 10 bytes of memory, which is illustrated here in this figure. So here I have a question for you. What happens if you try to put more than 10 characters in this buffer? Or will you be able to write more than 10 characters in this buffer? So any idea? Dear students, what do you think about this? If you have any guess or if you have any idea, you can share with me. Okay, so the answer to this question is yes. C will not stop you from writing more than 10 bytes of data into this buffer. So at this point, again, I have another question. If we are able to write more data into this buffer, then what happens when you write the data beyond the actual capacity of fixed size buffer? So again, if you have any idea and if you have any reply, any answer that you want to share with me, yes, you can share. Think over this and then give me any reply to this question. I'm waiting. Okay, so now let me explain The extra data spills into nearby memory locations, and that memory may contain other variables or even control data. So here is the illustration of buffer overflow. So here first we have created a buffer by writing jar name 10. So 10 bytes are reserved and 10 locations are available here in which we can store 10 characters. But when we are giving input, what we are doing here, we are giving input which is hello world, this is too long, and these are more than 10 characters. So in that case, what will happen? The first 10 characters will be stored in your actual buffer, which is allocated here, and the other characters which exceeds 10 characters length, those will be stored or override the adjacent memory locations, like which is mentioned here in red color. So hello world, this is your safe buffer, actual buffer, and this is too long. So these are the overwritten locations, adjacent memory locations. So 13 bytes are overflowed here. So here we have one of the very simple classic unsafe C code, and we have to focus here at this yellow line. We are using here getAce function. So getAce function is taking or reading user input without considering the size of the buffer. That makes possibility of buffer overflow. So many legacy systems still contain this kind of vulnerable code that may cause buffer overflow. Impact of buffer overflow can be realized from the fact that C does not enforce bounds automatically, which causes buffer overflow that can corrupt variables, crash programs, or open the doors to attackers. Now let's understand the impact of buffer overflow using this figure. At the bottom, we have created a buffer which has capacity of 10 bytes, and user enters 25 bytes. So see here, if user enters, practice makes us perfect. So what will happen initially, 10 characters will be filled in this buffer, and then memory which is above this buffer will start overwritten. And initially it override the variables on its stack, which may then contain wrong values, or they may contain garbage values. And if overflow continues, it may overwrite return address. And if it happens, that means your program may jump to malicious instructions, which is also called as a shell code, and it will crash or compromise. It may be crashed or compromised. So in this slide, we have tried to demonstrate the real-world impact of memory safety vulnerabilities, especially the buffer overflow. From historic Morris worm and code red to modern IoT botnets like Mirai, memory safety vulnerabilities have enabled global disruption, compromised millions of devices, and also compromised many critical industrial infrastructures. More precisely, it is very clear that memory safety is a root cause of major cyber incidents in systems that are developed or built using C or C++. Okay, so now let's discuss how to write safe C code to prevent buffer overflows. So one of the key safety principles in secure C programming is simply replacing unsafe C library functions with their safer alternatives. For example, use fgetAce instead of getAce. Replace strcpy with strncpy. Replace sprintf function with snprintf. And similarly, there are many other functions, like instead of using strcat, use strncat. So if we look, both of these functions are both of these categories. The functions which belongs to safe alternatives, they all are asking for size. So the another key safety principle to prevent buffer overflows is that always explicitly provide the maximum buffer size. And based on these two principles, let's have now look at the same code that we have discussed a little bit earlier. And here now we are using fgetS instead of getS function. And if you see here, by using fgetS and providing the buffer size, we completely prevent the buffer overflow. So now let's summarize our short lecture today. The first message that we got from this lecture is secure C coding is not optional in embedded IoT or safety critical systems. C gives you power, but with great power comes great responsibility. For example, C's direct memory access enables efficiency and high performance, but it requires careful programming to prevent vulnerabilities. And buffer overflows are preventable by using safe library functions. Never trust user or external input. Always check sizes, lengths, and boundaries before processing. And last but not least, is security requires a proactive mindset. So it is about building resilience from the start, not fixing problems later. So as an engineer, always remember that your code can save lives or your code can endanger them. So choice is yours. So before I wrap up, let's have a quick quiz to check what you have understood from this lecture. So the first question is, what is the safest standard library function to replace getS for reading user input? Second question is, why should you always check function return values, especially in memory and file operations? And the third question is, how can a buffer overflow in a network C program lead to remote code execution? So think and take your time to answer these questions. I will provide you answers to these questions in next class. So here is one last thing, which is a hands-on lab task. You are provided a code and you have to correct this code. So here's the description of this task. Fix the buffer overflow. The objective of this task is to replace unsafe C functions with secure alternatives. And you have to download this code from the course website and then find and replace all unsafe functions with their safe alternatives. And then you have to make sure to add the correct buffer size limits to each new function, compile and run your fixed program to test it, and then submit your corrected program along with your observation report. And the submission deadline for this task is next week. Thanks for your time and attention. If you have any questions, you can ask. Remember, secure C programming is not about fear. It's all about responsibility. So I look forward to work with you and developing safe, reliable, and resilient systems. Thank you.